Okay, we can go ahead.
Yeah. Okay. Good evening. So what I will do is we will try to do this thing in slightly in a different way. So what I will do is I will try to first tell you some kind of a definition of vector space, and after that we will not worry too much about the rigorous mathematical results, but instead what we can do is we can look at a few examples, and some examples together with the definition should be able to, and I will leave several things as exercise so that you can if you do those exercises, then you can get complete idea of what we are talking. So we have, first let us try to talk about definition of vector space. So we have two sets of vectors. First one is, I will call it as set of vectors. Okay, set of vectors. And then second one, I have something called set of scalars. Okay, so we have two sets and there are two operations. First one, I will call it as plus, and this plus is vector addition. These two are two binary operations, vector addition, and then you have some dot, which I will call it as scalar multiplication. Okay, now whenever we say we have a vector space, we have this algebraic structure in mind. Algebraic structure consisting of vectors, set of vectors, set of scalars with plus and then a dot. Okay, so whenever we say we have vector space, we have to have these four things. Okay, so an algebraic structure like this forms a vector space. Vector space, or sometimes we call it linear vector space, if I will divide this into two categories. First category of axioms is that the set of vectors with vector addition, that means the substructure of this, is an abelian group. Abelian group. Under this, what do we mean by this? That means you have, suppose let's say you have a vector v1 comma vector v2 in this space, then v1 plus v2 is also in V. Okay, that means if you add two vectors, you should get another vector in the same vector space. This property we call it as closure property. Okay, and second property is if you have three vectors v1, v2, v3 in V, implies v1 plus v2 plus v3 should be same as v1 plus v2, and that resultant vector is added to v3. That means the order in which you are adding is not important. Okay, so this property is called associative property. Associative property. Third, we have for all v in V, okay. Okay, maybe I should probably write. There exists a unique element which I will call it as 0 in V, such that 0 plus V is equal to V plus 0 is equal to V for all V in V. And this property is called existence of identity element. Identity element, or sometimes we call it as a null vector. Null vector should be there in the set. Okay. Fourth, for every V in this set of vectors, there exists a U in V such that U plus V is equal to V plus U is equal to 0. Okay. And we call U as inverse of V, inverse of V. So this is the property called the existence of inverse for all elements, for all vectors. Okay, sometimes we call it U as minus. Okay, so this is the fourth property. And the last property in this category 1 is that for every U V in V, U plus V is same as V plus U. So this is called commutative property. Okay, so any set with a binary operation satisfies up to 4, we call it a group, and including 5, we call it an abelian group. So that way, the first set of conditions is that V plus is an abelian group. The set of vectors is an abelian group compared to this one. Now, secondly, F is the field of scalars. Field is a technical word. There are certain axioms that it has to satisfy. But right now, let us understand that this is simply certain set of scalars. F is a field of scalars. Now, with respect to F and V, certain things have to be satisfied. So the first thing is, for any alpha in F and V in V, alpha times V has to be in V. This is closure under scalar multiplication. Closure under scalar multiplication. Second is that for alpha in F and U comma V in V, alpha times U plus V is equal to alpha times U plus alpha times V. Okay, so this property is called distributive property. So scalar multiplication is distributive. Okay, so this is the definition. You say any set which satisfies all these conditions is called a vector space. Okay, so it is easy to remember this way. So first set of condition is that this set of vectors will form an abelian group with binary operation called vector addition, and scalar multiplication has only these two properties. It is closure and distributive property. Okay, so not very difficult to remember this. Now, so if a set of vectors are not satisfying any of these conditions, then we say it's not a vector space. Okay, any of this not satisfying, we will say that it is not a vector space. Okay, now a couple of notions I would like to define so that we can take up solving some problems. So first concept that I would like to discuss is linear dependence and linear independence of a set of vectors. Okay, so this is one concept which I want to discuss. This is very simple to understand. So let us look at the vectors that we are familiar. Let's say I have a vector like this, which I will call it as a vector. Now let us say I have another vector which is along the same direction but slightly bigger vector, B vector. Now can I relate B to A? So can I get, if I'm asking a question, can I get B from A? So if I ask that question, the answer is yes. Because I can say B is equal to some kind of a alpha times A for some alpha in F. I can take a scalar and multiply the scalar with A, then I will get B. In this case, we say that these two vectors because I can write B linearly depending on A. So A and B are linearly dependent. Okay, so that is what we say. If we can obtain one from the other, we say that they are linearly dependent. Now let us look at another situation. I have a vector A, and let's say I have a vector B like this. It's not along the same direction. Now if I ask the same question, can we get B from A? The answer is no, because this is in a different direction. So along the if you multiply A with any other scalar, you will only get in this direction, right? So if this is another direction, that cannot be obtained from A. So we say that so here A comma B are linearly independent. That means I cannot get one from the other. Linearly independent. Now this notion, so we can use this thing. That means what? So B cannot be obtained from A, alpha times C. B cannot be obtained. Now formally we can say, suppose if I am saying I have some alpha times A plus some beta times B is equal to 0. This is called a linear combination of vectors, right? So let's say I have some linear combination of vector is equal to 0. Okay, this 0 is a 0 vector, right? This implies alpha equal to 0 and beta equal to 0. Only in this case, this whole thing can be equal to 0. Okay, suppose alpha is not equal to b. So how do you prove this? So let us say, so what I'm trying to say is two vectors A comma B are linearly independent implies if alpha A plus beta B equal to 0 implies alpha equal to 0, beta equal to 0. Suppose, let's say we will write a small proof for this. Let's say that if alpha is not equal to 0 and beta is not equal to 0, but alpha A plus beta B is equal to 0. Okay, so what does that mean? That means I can write down alpha times A is equal to minus beta times B, or A is equal to minus beta by alpha times B. What did we get here? This implies what? A and B are linearly dependent, because this is one scalar, this is some scalar, right? Linearly dependent. But we started with a premise that they are linearly independent. But if you make alpha and beta non-zero, then it gives you that they are linearly dependent. So the only way that this linear combination is 0 is by choosing the variables from the field to be 0. In any other way, we will not be able to get this one. Okay. So this is, we can now generalize this one. Okay. So a general definition now we can provide general definition vectors a set of vectors, let us call them as v1, v2, etc. vn, are linearly independent if alpha 1 v1 plus alpha 2 v2, etc. alpha n vn is equal to 0 implies alpha 1 is equal to alpha 2 is equal to alpha n is equal to 0. That is the only way in which this whole thing can be 0. Okay. Otherwise, the set of vectors is linearly dependent. Okay. So that is what is a definition. And we can also evaluate this one depending on our given vectors. Okay. Now let me talk about suppose you take a plane. Okay, so let's say consider xy. Okay, consider xy plane. Now on an xy plane, so let's say I have an xy plane like this, xy plane. Now let's say that I have a vector A, and let's say I have another vector B. Okay. Now A and B are, as we have discussed already, they are linearly independent. Now let me draw another vector C here. Now, so we know that A comma B are linearly independent. Now the question that I am asking is, are A comma B comma C, these three vectors, are these vectors also linearly independent? That is the question that I am asking. So what do you think? If I have three vectors,
No, sir.
they are not linearly independent. Why? Because you can always obtain C from A and B, or B from A and C. Any two of them are linearly independent, right? So on a plane, maximum number of linearly independent vectors is equal to 2. Any other vector can always be written as a linear combination of these two. For example, C can be written as some alpha times A plus some beta times B. So C depends on A and B. So when you take three of them, they are not linearly independent. Two of them, yes. So there is a concept called the maximal set of linearly independent vectors. Okay. So for a given vector space, V, even though sometimes I write V, but we should understand that when I say V has this F defined, plus defined, and this entire algebraic structure. For a given vector space, maximal set of linearly independent vectors maximal set of linearly independent vectors is called the basis of vector space. Basis of vector space. And number of elements in the basis defines the dimension of the vector space. Okay. Now we can understand this concept a little carefully. So suppose if you have a two-dimensional plane like this, XY plane. Okay. So let us say I have a vector I cap and I have a vector j cap. So I cap and j cap are linearly independent. Okay, they are linearly independent. Now you take any other vector, which I will call it as some v. I can write down this v as some, okay, I can write this as some alpha times I cap plus beta times j cap, correct? And these alpha and beta are called x component, y component, and things like that, right? So alpha and beta, they belong to this F. So I am going to propose a very useful notion. Okay, so I will call this as a useful notion. Number of scalars required to define an arbitrary vector of V is the dimension of the vector space. Dimension of V. Like for example, here in plane, if I want to define a vector, how many scalars are required? I require two scalars, x component and y component. So the number of scalars is 2, so the dimension of this vector space is 2. Okay. Now, why I am saying this is a useful notion is because in some other abstract vector spaces, using this notion, it is easy to recognize the dimension of a vector space. Okay. So that is what. So I have now defined what a vector space is, what is linear independence, what is linear dependence, and what is basis, and how to identify the vector space, dimension of the vector space. Okay. Okay, so now what we will do is we will try to quickly go through some examples. Okay, so let me just present a set of examples. Just try to is it readable, whatever I have?
Yes, sir.
Yes, sir.
make slightly bigger. Okay, so just can someone read to just make sure that you have understood, you are able to read? Check from that, can you read?
Yes, sir. Check if the following set of elements from a vector space.
If they do,
If they
find
do,
the
find the dimension and obtain trivial basis. If they do not identify, which axiom is not satisfied.
Okay, very good. So now let us just try to, I will argue some of them and some of them you can write for yourself. So let us say, first thing is I have set of real numbers. Okay, set of real numbers. Now, note one thing that so let us say A. So before we do this, first let's understand that this F, the field, is either real numbers or complex numbers in most cases. In most cases. There may be some exceptions, but at least in all these examples that we have here, it is either real number or complex number. Now let's look at set of real numbers. Okay. So that means if I want to write it as an algebraic structure, how do I write? Algebraic structure is basically vectors also real numbers, scalars also real numbers, plus, and plus is a usual addition of real numbers, and this is just a multiplication of real numbers. Now, is this a vector space? Now, if you look at, all the axioms will be satisfied. Okay. Now, to define a real number, how many real numbers are required? One real number, right? Whatever real number you want to define, take that real number, right? So, to define a real number, we need one real number. So what is the dimension of this vector space? Dimension of this vector space is simply 1. Now, some trivial basis, that's what we are. So trivial basis in this case is, there should be only one element, right? That is 1. Because you are going to take any real number, multiply with 1, then you will get the same real number. So the trivial basis element is just 1. Okay, is this clear or any doubt in this? Okay, so then the second one, B, we have set of complex numbers over a field of real numbers. So what does that mean? My algebraic structure is, I have complex numbers, real numbers, plus, and this also forms a vector space. Okay, so you can check with all the axioms. It will satisfy all the axioms. Now to define a complex number, okay, so to define a complex number, how many real numbers are required? Two real numbers are required. Two real numbers are required. So what is the dimension of this vector space?
Two only.
So the dimension of this vector space is 2. So what can we write about a trivial basis for this? I must write two complex numbers.
So 1 plus or minus I?
So two complex numbers is 1 plus 0i and then 0 plus I, right? So you multiply a real number with this and another real number with this. So let's say a times 1 plus 0i plus b times 0 plus I will give you a plus I, such that a and b are in real numbers, correct? So these are the two complex numbers which can be served as a basis of this. Okay. Now third one is set of complex numbers with the field as complex numbers. Here we have set of complex numbers with the field as, so what is third one? I have complex numbers plus and multiplication. So now let me not write all these sentences. So we will directly try to ask what is the dimension of this vector space.
Four.
Why 4?
Sir, each complex number have two real number parts.
But see, that is why I want you to understand this carefully. What was the definition that, what was the useful notion that I have talked about here? Number of scalars required to define an arbitrary vector of V is called the dimension, right? Now, what is the set of scalars here? Set of scalars is also complex numbers and set of vectors is also complex numbers. So to define a complex number, how many complex numbers are required?
One.
One, right? So this
Yes,
is
sir.
exactly like real case. So dimension is 1.
Yeah.
Correct. So what
Yes,
is your trivial basis?
1 or
Just 1. Correct. So dimension is 1
yes,
and
sir.
your trivial basis is just 1. So this is
Sir,
the C is like A only. Correct. Real and real is one dimensional. Complex is also one dimensional.
sir,
Okay. Yeah.
can you repeat this, sir?
See, complex number, to define a complex number, I require only one complex number. Correct.
Yes, sir.
So that means it is only one dimensional. So you take a complex number, multiply that with 1, you will get that complex number. That's all.
Okay, sir.
Correct. So in this D, I am now talking about set of positive real numbers. Okay, so in the D, I have set of positive real numbers, which I will call it as R plus, and then scalar is R and plus and so on. Now, is this a vector space? First of all, So is this a vector space?
No, sir.
Which axiom is not satisfied?
Inverse is not.
So there is no inverse. Okay, so no inverse elements. So it's not a vector space. Okay, so this is D1. Okay, so it is not a vector space. Okay, now you look at second part of that D. Set of positive real numbers. Now I am going to redefine my vector addition and scalar multiplication. Okay. So now in this second one, I'm saying, okay, the same thing, R plus R. Now let me call this as so same thing like this, but I'm going to say that X, Y in R plus, okay, the vector addition, that is X plus Y, means it is X into Y. And let's say some A is in R and X is in R plus. A dot X, scalar multiplication, is X to the power A. Okay, so that means vector addition and scalar multiplication are redefined. Okay, now you can verify for yourself, this will form a vector space. Okay, so then it is a vector space. It is a vector space, and of course the dimension is 1 because you require only one real number, right? It's a one-dimensional. Correct. So this is, so that means if something is not a vector space, then by appropriately redefining those vector addition and scalar multiplication, we can think of making it a vector space. Okay. Okay, so now let me take another. So up to this, these are just basically A to D. These are simply some sets. Okay. Set of real numbers, set of complex numbers, and things like that. Now, these are things which are depending on another concept. Okay. E, F, G, H. So first thing is set of all functions where a function is defined from a set of 5 donkeys to real numbers. Okay. So let's try to understand this. E. My vector space is set of all functions such that F is function from set of 5 donkeys to real life. And now I am considering all such functions. Okay. So how many such functions will be there? There will be infinitely many such functions because you can have anything. No, so let's say that I have a set where I have donkey 1, donkey 2, donkey 3, donkey 4, and donkey 5. And then I have a set of real numbers here. So donkey 1 is mapped to some real number, donkey 2 is mapped to some real number, donkey 3 is mapped to some real number, some real number, and some real number. So this is one function. Now like this, I can have mapping to any real numbers. So I will have infinitely many functions. So this f has, just like even set of real numbers are infinity, set of complex numbers are infinity. Okay, so V has infinite elements. Okay, so V has infinite elements, which is also true in the examples that we have discussed earlier. Okay, so now my question is, you can show that it will form a vector space. Now, what is the dimension of this vector space? So, what the dimension of this vector space? Abhijit, what is the dimension?
Sir, I think it is 1 because it is related only one time.
Okay, so how do we do the analysis? So we have to ask what is the general vector? So first question is, what is the general vector? Second question is, how many real numbers are required? How many real numbers are required, needed to describe the general vector? Correct?
Yes, sir. So it will be like 5 means 5 donkeys to 5 real numbers.
Exactly.
So
the
5
vector space is 5. Because for every donkey, we have to associate one real number.
Means I didn't think that would be so easy. I thought it should be either 1 or infinity.
So there are 5 donkeys. So essentially, what is the general vector here? General vector is something like this, right? So it is like, let's say x1, x2, x3, x4, x5, where these x1, x2, x3, x4 are real numbers. Correct? So xi are real numbers. This is the general vector. So I require 5 real numbers. Correct? So this
Yes,
is
sir,
just
yes,
kind of changing the language. But once our concept is clear, the language will not affect us. Right? You may call donkeys or monkeys, it doesn't matter.
yes, sir.
Okay.
I
Now
was
I have.
confused by the language.
So that is the reason why I am changing the language, so that you should get out of this dependence on the language. You should be linearly independent from language. Okay, next is set of all straight lines on a plane. Okay, so let's call this as F.
Sir.
Yeah.
So trivial basis for that previous one, sir.
So what it will be? Okay, so let us ask what is trivial basis. So the trivial basis is like donkey 1 has 1 and all are other zeros. This is one vector. Then donkey 2 is 1 and all others are zeros. 0, 0, 1, 0, 0. 0, 0, 0, 1, 0. 0, 0, 0, 0, 1. So these 5 vectors are the general, the trivial base. Is it clear? Every donkey is showing 1 and all others are showing 0 is a function, right? So that is what forms a basis vector.
Sir,
Correct?
sir, is this the real number which is contributing to dimension?
The number of real numbers required to define a general vector is equal to the dimensional vector space. So to define a function, I must assign some real number to every donkey, right? So there are 5 donkeys, so I require 5 real numbers.
Okay.
So that is the dimension. Okay. So now, yeah.
Sir, if we think of this function, if we think of f as real valued function, so there can be infinite such functions. And if we see it as being expanded in Taylor series or something, there can be infinite bases. Not the bases, the elements in the bases.
Yeah, but so for expanding it in the Taylor series, you must have certain property of this function, right? It should be differentiable, it should be continuous, and all those things, right? But this function is basically you have a domain which has discrete elements, 5 discrete donkeys, and for every donkey you are going to associate a real number. Correct? So the nature of this, even though, see, normally what do we say? A function is just a map, right? From some set to another set, correct? And if the set is a continuous function like real number to real number, then you can say it is a function of x, and x is a real number, f of x is also a real number. Okay, so such continuous functions only we can do Taylor expansion, correct? For any map, we will not be able to do Taylor expansion. Is that clear?
Yes, sir.
Yeah. So these functions are not such continuous functions. This is just like a map. From some set to another set, we can define a map and consider set of all such maps. Okay, so now in this example, I'm going to consider set of all straight lines on a plane. Okay, so how do we handle this?
So is it 2?
Why 2?
Means x and y, and the straight line we can define it with 2 coordinates.
So let's say that I have one line like this, another line like this, another line like this, another line like this. Now consider all possible lines that I can draw on a straight on a plane. Okay. Now to define a line,
Yes, sir.
I require infinite x and infinite y values.
Yes,
Correct?
sir.
All the values of
Yes,
x,
sir.
all the values of y, I require to know. Okay. So if you want to talk about, I will give you x values and y values. There are infinitely many of them I require to draw a line. Correct?
Yes, sir. Yeah. So,
but what actually defines a line? Given that x and y are available to you, okay, a line requires infinite values of x, infinite values of y. That means whole of x and whole of y are available. Now, what defines a straight line?
Slope and intercept.
Slope and intercept, because you can say that your y is equal to mx plus c, correct? Mx plus c. Now, if you define your m and c, you define a straight line, right?
Yes, sir.
Now,
Yes, sir.
given the whole of x and whole of y for you, to define a straight line, how many real numbers are required?
Here in the case 2.
2 real numbers are required, right?
Yes, sir.
So what is the dimension of this vector space in that case?
2.
Just 2. Because
Yeah.
you require 2
Lucky.
real numbers.
Calculated this.
Yes. Now you ask a question. What should be the trivial basis for this?
One zero zero one.
So I want to understand that. See, now here an element is a straight line, right? Okay, so understand that here a vector is a straight line. In the previous example, vector is a map. Here vector is a straight line. That means basis vector also should be straight line, no? So tell me the equation of those 2 straight lines which can be considered as a trivial basis. I mean, whatever your answer is correct, but I'm only asking you to translate it into straight line equation.
Y equal to 1, x equal to 1.
Yes, sir.
See, all the equations should be y equal to something, not x equal to 1.
So
Y is equals to mx and y equals to c.
But m and c are real numbers, right?
I mean, the one is with the x coefficient and other with the constant, like.
Correct. So suppose if you say that this vector, a general vector, you write it as mc. Okay. So then what will be the basis? Basis corresponds to 1 0 and 0 1, right? So 1 0 means what? M is 1, C is 0. That means y equal to x. And 0 1 means M is 0 and y is equal to. These are the 2. That means if you have xy plane, so this is one line. This line is y equal to 1. And then this is another line, which is y is equal to x. So these 2. So any other line can be written as some alpha times this and beta times that. Correct? So these are the 2 straight lines which can be considered as the trivial basis. Okay, so we have to write down the basis also as a what is called a straight line. Whatever is the vector, in the same language we must depict this basis also. Now,
So-
why I'm
So in this case, how are the operations defined? Addition and multiplication?
So when you want to define, suppose let's say I have 2 straight lines. So one straight line is M1 C1, another straight line is M2 C2. Okay, M2 C2. So what happens when I add them? I will get M1 plus M2 C1 plus C2. Okay. Now how do so I understand your problem, your question was how to visualize that one. Okay, so let's say that I have a straight line like this, and I have another straight line, let's say like this. Now when I add these 2 things, what happens? Adding means what? I am adding point by point. For example, let's say this value of x, this is the value and this is the value. I add these 2 things. When you do, you get a new line whose slope will be m1 plus m2 and y-intercept will be c1 plus c2. Okay, so that is how they get added. So geometrically, you add point by point, or you add values of y at every point, and then it turns out that the slopes get added, intercepts get added. So that is how we can add these two lines. Okay, is that clear?
Yes, sir.
Okay, so now we can go to G. G has two parts. Set of all polynomials of order less than n. Okay, so if you want to, you can go step by step. First, let's say that G, let's say 1, set of all polynomials of order less than n. Okay, so in this language, the set of all straight lines can be considered as set of all polynomials of order less than 2. Correct? Less than 2 means up to order 1. So that means y equal to c plus mx, right? So so the previous, so n is equal to 2 gives, what was this one? F, I think, right? Gives f. Do you see this? N equal to 2 gives f. Now, it is not very difficult to suppose if you take n is equal to 3. That means what? That means my vector will be some a0 plus some a1x plus some a2x square, such that a0, a1, a2 are in real numbers. Okay, so is it easy to find out what is the dimension now? How many real numbers are required to define a quadratic curve like this?
3, sir.
3. Very good. So the dimension is 3. So for this set of all polynomials of order less than n, okay, so what will be the dimension?
N, sir.
So this is dimension n. Correct? Okay, now let's look at 2 under G. Set of all polynomials.
Sir, I have a doubt. What happens if n is equal to 4, sir?
N is equal to 4, you will have to write down. So let's say n is equal to 4. So what will be your vector space? Your vector space is a0 plus a1x plus a2x square plus a3x cube, such that a0, a1, a2, a3 are real numbers. So how many real numbers are required?
4.
4 real numbers are required. So dimension is 4.
Oh, so it depends upon the n. Like,
Yeah. Yes. So it is actually equal to n. So the dimension is
okay.
n.
Yes, yes. Now understood. Thanks.
Yeah. Now, when you consider a set of all polynomials of any degree, order can be anything, okay? All polynomials of all orders. So what will be the dimension of that vector space?
Sir,
There is
means
no
all,
restriction. Yeah, all polynomials.
all polynomials.
Yes.
So,
Infinite.
It's infinite, right? So I haven't defined any order. So the dimension is infinite. So we can have vector spaces whose dimension can be finite, whose dimension can be infinite. So first time we are coming across an example where the dimension is infinite. So please keep this in mind. We are having only one x and one y, or one x, it's only a function of x, y. Okay. So if you want to write basis for this, okay, basis for set of all polynomials, we can say 1 x, x square, x cube, etc., 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 and all powers of x. This basis is called monomial basis because each one of them is called a monomial. It's not a polynomial, but it's a monomial. It's called a monomial basis. Okay. So someone asked earlier, basically Taylor expanding any function is like expanding it in this basis, right? So any function will be written as some constant plus something, some constant times x plus some constant times x square, etc., etc., etc. So Taylor expansion is essentially expanding a given function in the monomial basis. Okay, so good. So now what we will do is we will go to the next set of examples. Okay, so this next set of examples is from H to M. Okay, this is a different class of examples. Okay, this is with respect to, so in each of these examples, I have shown a different class of vectors. Set of vectors are different. Okay, so now H, I, J, K, L, M, we are going to deal with 2 by 2 matrices, but then they are different 2 by 2 matrices. The sets are different. Okay, so I think we are now at H. So I have set of all, so my vector space is set of all 2 by 2 real matrices. So what is a vector here? Vector here is a 2 by 2 matrix. Now tell me, what is the dimension of this vector space?
So is it 4? Because we have 4 real elements.
Very good. So it is 4 because we require 4 elements, right? 1 1 element, 1 2 2 1 2 2. 4 elements are required. Correct?
Yes, sir.
Nice. So what will be trivial basis in that case?
Sir, will it?
1
Sir,
0 0 0
1 0 0 0
0 1 0
0 0 0 0 1 0 0 0 0 1. Correct? So that is our H. Okay. Now set of all 2 by 2 matrices H I, set of all, now vector space V is set of all real symmetric 2 by 2 matrices. What do we mean by symmetric matrix?
A is equal to A transpose.
A is equal to A transpose. Implies A is symmetric, right?
Yes, sir.
Oh, okay. So what will be a general, okay, a general 2 by 2 real symmetric matrix? How does it look like?
A, B, B, A, like it's like two elements, dimension
A,
2.
B,
B, A.
B, A. Should it be A?
Minus A.
No, if I write some C,
No,
what
sir.
will happen?
No. Nothing. Yeah, we can write. Yeah, correct.
You can write, right?
Yes, we can write.
So this is the most general symmetric matrix. Only this has to be same. B and B has to be same. These two can
Yes.
be different, right? So what is the dimension
sir.
of this matrix? This vector space?
3.
sir.
Dimension is 3 because I require 3 real numbers, correct? So what is the trivial basis?
4, sir.
Why 4? I require 3 real numbers, right? A, B, C.
1 0 0 1 0, like 0 1 1 0 0
1
0
0
1.
0 0
0 0 1 1 0.
0 1 1 0.
Then 0 0 0 1.
That's all. So these 3 are the 3 real matrices. Now let us look at set of all real anti-symmetric matrices. Anti-symmetric 2 by 2 matrices. What is anti-symmetric matrix? A transpose is equal to minus A. Okay, what is the general antisymmetric matrix?
AB minus B, C.
AB
Minus B, C.
general antisymmetric matrix. What did you say? AB minus B, C. So if you take transpose, what will you get?
Minus A.
So will you
That
get
is
minus
A
A?
minus B, B, C.
Okay, so let us say A is this, then A transpose is A minus B, B, C, right? Is this equal to minus A?
Oh, then A and C also should have minus.
How will where if I have minus here?
No, like in the real A itself, we need to add minus A and minus C too, so that the transport becomes minus A.
Even if I put minus, minus will remain here. No, it will not become minus here, right?
After that, we can take it out.
If you take it out, then minus will not be there inside.
Yeah.
So let us say that A is equal to, let us put all the elements A, B, C, D, and A transpose is equal to A, C, B, D. Now I want A transpose is equal to minus A. That means now my A, C, B, D must be equal to minus A, minus B, minus C, minus B. Okay. So if two matrices are equal like this, what does it mean?
The diagonal element has to be 0.
So that means element by element it should be same, no? That means A is equal to minus A, C is equal to minus B, B is equal to minus C, and D is equal to minus D. That is what I am getting here, right? So C equal to minus B, B equal to minus C is fine. This is okay. But A is equal to minus A. What does that mean? You take this minus A this side, 2 times A is equal to 0. 2 is not equal to 0, and hence A has to be equal to 0. Same thing is true here. D has to be equal to 0. So the most general antisymmetric matrix is like this. Okay, so most general 2 cross 2 antisymmetric matrix is equal to diagonal elements have to be 0 and off diagonal elements have to be negative of each other. So what is the dimension of this vector space?
One.
Just one dimensional vector space. You require only one. So what is the trivial basis element?
0, 1, minus 1, 0.
0, 1, minus 1, 0. Just only one matrix because it is a one-dimensional vector space. Okay. So that is okay. So now let's look at K. Now set of all, your V is set of all 2 by 2 singular matrices. 2 by 2 real singular matrices. Real singular matrices. What do you mean by singular matrix?
Sir, sorry, sir, forgot.
A matrix A is singular.
Determinant of A should be.
A singular implies determinant of A is 0. Correct? Non-singular means determinant of A is not equal to 0. Correct? Now, first of all, we can ask the question, is this a vector space?
No, sir.
Why it is not a vector space?
So it's not closed.
It's not closed. So give me an example. Okay, what is your name? You are showing ABCD. Is it a abbreviation of your name or first 4 alphabets?
So my name is Sonal.
Huh?
So that's my default.
Okay, what is your name?
Sonal.
Okay, so give me an example where the closure is not satisfied.
So we can have 1 0 0 0 and 0 1 0 0.
0 1 0 0. Okay.
Yes. So when we
1
add
0
them,
0 1 0 0. If I add, what will I get? 1 1 0 0. This is determinant is 0. This determinant is 0. This determinant is also 0. So it is closed, no?
Sir, the inverse will not exist.
But inverse we don't require What is the inverse we are talking about?
Sir,
Additive inverse.
additive inverse. Yeah, sorry, sir.
I think what your answer is correct, but only this example is not correct. So instead of this, you take like this 1000 plus 0010. So 0001. This is singular matrix. This is also singular matrix. But what is this matrix? So this is singular. And this is singular. But this is non-singular. Correct? It's an identity matrix. This is not singular. Follow? So you can see that the closure is not satisfied. So inverse is not a problem, but the closure is not a problem. Closure is a problem. So not closed implies not a vector space. Same thing is true with the next one, L. Set of all non-singular matrices. Non-singular. It's also not a vector space. Okay, for example, you take 1001. This is non-singular. Plus 100 minus 1. This is also not singular. Non-singular. So when you add them, you will get 1000. This is singular. So it is not closed. Implies not a vector space. Okay. Yeah. So okay, I think I have done up to that. Then we have next level of examples. So I would like you to try this NOPQ up to this. These are also with respect to matrices, but of a different order, n by n, 3 by 3, like that. So please try this. Try these things. And then the remaining ones we will do in the next class. You can try this also, remaining ones, but I will discuss R, S, T, U, V, W, those things in the next class. Okay, so I will stop here. If you have any questions, you can ask.
So why is this called linear vector space?
Because see, the linear structure is there. So linear dependence, linear independence, right? So when we are talking about combining them, they are combined linearly. So basically, the linear vector space and vector there is no nonlinear vector space. So basically, linear vector space and vector space are same. Vector space structure is always linear structure.
Sir, then what is non-linear dynamics, sir? Like, means I heard that word somewhere.
Yeah, nonlinear dynamics is different. Nonlinear dynamics, see, basically, if you say that your force depends on your coordinates in a nonlinear fashion, then the underlying dynamics, when you solve Newton's equations, the underlying dynamics is called nonlinear dynamics.
Okay, okay.
Sir?
Yeah.
Sir, can we physically interpret this linear vector space?
See, linear vector space is a mathematical structure on the set of vectors that we have. Okay. Now, it turns out that in many physical problems, this mathematical structure is very useful. So one of the examples that I was talking is, suppose if you have polarization of an electromagnetic wave, the polarization states will become, set of all polarization states will become a complex vector space, a complex set of complex, it's basically a two-dimensional vector space defined on complex numbers. In the same way, every physical system in quantum mechanics, the set of all states will become a vector space. So the vector space structure is always useful. For example, if you have set of all periodic functions, then cos function, sine function will become a basis for the set of all periodic functions. And then you apply, when you expand a periodic function in this, you will get what is called Fourier series. Okay, so like that, this structure is useful in many, many physical problems.
Okay. Okay.
Sir,
Sir,
is vector space is like a set, sir?
Yes, it is set of vectors with some properties and axioms that it has to satisfy. There is a structure on that set.
It doesn't need a direction, right?
See, that is what I am trying to show here. See, vector is a very general concept. In this case, in some examples, I have my vector to be a matrix. In some examples, I have my vector to be a polynomial. In some example, I have my vector to be a map. In some other, I have my vector to be a straight line, right? So a vector is not always a magnitude and direction, right? So vector can be some general set. An element of a set is a vector.
Can we have a physical representation for this?
Physical representation for what?
For vector space.
See, vector space, as I told you, this is a set, a mathematical set with some structure. Okay. Now, this structure is useful in describing physical systems. Like all systems in quantum mechanics, polarization degree of freedom of electromagnetic waves. Okay, so like that. So you have to see where it becomes relevant in physical system. And if you say that if a vector is physically relevant, that means that is what defines. For example, the polarization of a photon or polarization of an electromagnetic wave is a complex vector. That means any complex vector can represent a possible polarization state of your electromagnetic wave. That is what the physical relevance that we can think of. For example, if I have to extend your question, that what is the physical realization of a real number, like that, if you can ask, what do you say? Okay, I measure position of a classical particle, it is a real number. I measure momentum of a particle, it's a real number. So to that extent, real numbers are physical because measurement results are real numbers. Okay, so in the same way, the vector space is also physically relevant because many physical systems, their states are elements of the vector space. Okay, so there are no questions. We can close.
Shall I stop the recording?
Yeah.